Okay, I was going to change the plans for this weekend, or I came up with an idea and I changed plans to do a lab, and it ended up being an epic fail after I put a lot of hours worth of work into it. Maybe later. Depends on the availability of materials and price, and I tried to make my own and it didn't pan out. Managed to make a mess and stink the lab up though. That's always a success, I suppose. Well, let's go on then, since that's not going to happen, and talk about resonance. And so we're on page, I don't know, 66. Consider the allyl carbocation. So the carbocation, well, let's not worry about that too much. You got a positive charge on one end and a negative, or a double bond over here. And all three of the carbon atoms are sp2 hybridized. So that one's sp2 hybridized, got a double bond. That one's sp2 hybridized, got a double bond. This one is too, because it lacks a hydrogen, basically. Well, you could draw this guy, carbon, 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 like so, with all the sp2 hybridizations. You know, in a plane, you've got three bonds sticking out. And then you got p bonds with nothing in them. Those p bonds could pair up here and here and make, with this sigma, your pi, let me try that again. They could pair up here and here and you'd have a pi bond that makes your double bond on this side, or they could pair up here and here and make your pi bond that makes your double bond on this side. And what it does is it acts like it could do both. The book draws it like this. Now, sometimes people explain this as if it is flipping back and forth between this way and that way, its mirror image millions of times per second. But that's not really quite what happens. It's just that this bond has some double bond character, and so does this one. And this bond has some single bond character, and so does this one. And it behaves as this end of the molecule has some positive charge and this end of the molecule has some positive charge, all at the same time. So this gets into what we've talked about before called molecular orbital, MO bonding. So the whole thing, what's going on with an electron up here, is affected by and affects all the way across the molecule. So you have an anti-bonding molecular orbital, which means if you run the math, you get no constructive interference here. Now, remind me, if I haven't taken a spring and stretched it across the room and showed you constructive and destructive interference, I'll discuss that, but I think we have. And a non-bonding molecular orbital, so the math doesn't show this working out, but you have constructive interference when you run it this way with a bonding molecular orbital, with the pi electrons. So this is what we expect because it's bonding molecular orbital. I think I can increase the size of that a smidge. Nope, I don't want to do that because it screws everything up. Okay. Now, curved arrows going on to page 68. If you're hung up on this, I should explain it for another half hour and you'd probably still be hung up on it. It's okay. Let's move on. You'll get that one day maybe. If you go to page 68, we've got curved arrows, which I was going to use in my lab. The lab is really cool, but it fell on its face. And show how charges, lone pairs, can move around. And there are two rules that are pretty simple. One, avoid breaking a single bond. And two, never exceed an octet for second row elements. For example, see if I can do this. You can, with sulfur, which is in the third row, have more than an octet. End up with more than an octet. Sulfur has 6 valence electrons. 1, 2, 3, 4, 5, 6. But it can have an expanded octet. It can end up with 10. 2, 4, shared 6, 8, 10. It's the expanded octet. We did some Lewis structures with expanded octets last year. You can't do that with oxygen, the rule says. As a matter of fact, let me pull up last week's, and you did this, Lewis structure stuff on chemistry, and I'll show that to you. There's some Lewis structure stuff. Nitrogen here has an octet. Nitrogen there has an octet. Nitrogen there has an octet. But it's a second row. Octet, octet, carbon. Carbon has an octet, ends with an octet. But if you go off of some weird things, there's sulfur has an octet. Chlorine can, and it's in the third level, the third row of the periodic table, can have an expanded octet. 2, 4, and shared pairs, 6, 8, 10. Sulfur. Well, phosphorus could have an expanded octet, 2, 4, 6, 8, 10 that are, once it's done sharing. But phosphorus is in the third row. Here's one where sulfur could have 12 shared pairs, 2, 4, 6, 8, 10, 12. An expanded octet. Maybe you kind of remember seeing those now. But these guys can't in the second row. Why not? Okay, I'll tell you. Because when you get to the third row, there's 3 d orbitals down inside. You can put electrons down in those if you have to. You can take electrons out of them if you have to. That gives you a bigger atom, more flexibility. You're farther away from the nucleus. Individual charges don't matter as much, and you can shuffle charges around and have expanded octets. You're missing those d orbitals with second row elements, and you have fewer electrons to play with, so you can't pull that off. Remember the rows that you're in. Okay, or the families, groups that you're in. Okay, so here's an example of a bad arrow. This is a bad arrow. I don't know what page this is from. This is right out of your book. The top of page, we're on curved arrow, starts on page 68. Now, turning the page, we've got 1, 2, 3, 4 bonds on carbon. That's 8 electrons. It's what you're supposed to have. If you move this pair of electrons in here, you'd have 5 bonds, because that pair of a lone pair of electrons would become a double bond. If you take a double bond apart, one of them, you'd get a lone pair of electrons out. And you can't have 5 bonds on carbon. You're limited to 4. Okay, with nitrogen, nitrogen is here, has 5 valence electrons, can take a maximum of 8, and that's it can't have an expanded octet because it's in the second row. There's my 2, 3, 4, 5. With shared electrons, I have 2, 4, 6, 8. I can't put a lone pair in here and make another double bond because that'd be too many electrons around nitrogen. I can't move this arrow in here because then oxygen would have 2, 4, 6, well, the amount that oxygen brings to the table is 2, 4, 5, 6, but in terms of shared pairs, it's got 2, 4, and those are shared, and those are shared, it's got access to 8. If I try to put another lone pair in there, I'd have too many electrons around that oxygen. It's not going to work. So why is this arrow bad? Well, because if I did this, don't forget that's a carbon there. And that carbon already has 2 hydrogen off of it and another bond over here to another carbon, so it's got 8. If I put this shared pair in there, I'd be trying to put 5 bonds on carbon, which is a no-no. And I've done it many times, but it's a no-no. Okay, now there was a little bit farther down that page, because it came up in class, is can you take this double bond, take that bond out of there, and put a lone pair up here? Yes, you could do that. because then the oxygen ends up with 2, 4, 6, and one's, it brought one in there with 7, and there's a share to an 8. Yes, you can do that. That oxygen's got 8, but let's look at this carbon down here. Carbon went from 1, 2, 3, 4 down to 1, 2, 3. Oh, but you can do that. You can have not as many electrons as you'd like, but you can't have too many. And by the way, this wouldn't be stable. With that positive charge and that negative charge, I think it's going to go right back to this. But it's possible. Okay, so going through 2.21, as you turn to page 70, determine whether each curved arrow, okay, what you ought to do is pause at this time and try some of them rather than just watch this through. But for each of the problems below, determine whether each curved arrow violates either of the 2 rules and describe the violation, if any. Don't forget to count all hydrogen atoms and all lone pairs. Well, the first one you can't do this because you can't have 1, 2, 3, 4, and then put moving another one in there. 5 bonds on nitrogen. Nope. What about this one? Yeah, you could do that one. You'd end up with a negative charge here and a positive charge down here, but you don't have too many bonds on anything, and you didn't break a single bond, you broke a double bond. So this does not violate either rule. Number C. Okay, I have right now on this carbon 1, 2, 3, 4 bonds. If I try to move that double bond in there to have 5, that's not going to work. Okay, what about this one? I have 2, 4, 5, or I'm sharing 8. If I put that in there, I'd have too many bonds on my oxygen. So you can't have that many bonds, and you can't have 3 bonds and 2 lone pairs on oxygen. I'd put too many electrons around it. So this violates the second rule by giving 3 bonds, 1, 2, 3, and 2 lone pairs to an oxygen atom. Okay, what about this one? Well, I already have 4 bonds on this carbon. If I move that electron pair down there, I'd be trying to put 5 in, and you can't do that. Okay, so if I move this bond to here, now that looks appealing because you look at this and you say, well, these are all the same. But that's not the case, because I have 1, 2, 3 bonds here and a hydrogen there as my 4th one. Here I have 1, 2, 3 and a hydrogen here as my 4th one. Here I have 1, 2 and a hydrogen and a hydrogen. I've got my 4 bonds. If I try to move this in there, I'll make a 5th one. To a carbon atom, and the one I'd be trying to give 5 to is that one right there. Okay. What about this one? I can't break a single bond and have no bond. In this case, at least. You can break bonds, single bonds sometimes, but not to do this. And that wouldn't be a resonance thing. That would be happens in a reaction thing with another reactant, which is separate. We're talking about resonance here. Nothing else coming in and doing a reaction. Okay, violates the second rule. Okay. Well, yeah. This rule gets violated too. There's 1, 2, and hydrogen, 4 bonds up there. If you could put those up there, you'd still be putting 5 on it. And you're breaking a single bond. Okay, what about this one? Well, you'd be breaking a single bond here. And this carbon already has 1, 2, 3 hydrogen off of it, plus this bond, you'd be putting 5 on there. Okay, what about this one? Well, I think we might be all right to do this one. If we break that bond, nitrogen will have 2, 4, I think we're okay on this one. What am I missing? Anything? No, doesn't violate either rule. The problem in breaking bonds is not usually, or making bonds is, well, it just depends, I guess. Never mind. What about this one? Could I move electrons out of here? I think so. Unless I'm missing something. Doesn't violate either rule. Okay, now you gotta watch this carbon here because it has bond, and a hydrogen you don't see, and a hydrogen you don't see. There's already 4, you'd be putting a 5th one in there. What about this one? Put that in there. Well, again, there's a carbon here with 3 hydrogen off of it, and you'd be giving it a 5th bond. Okay, 2.22. We want to know about moving an electron. So we want a curved arrow. They could only be put in one location without violating the rules, and the place you could put it is here. You could move that electron up to there and make a double bond. Or I'm sorry, put two lone pairs up here. And that would change that to a negative, by the way. I think 2, 4, no, guess not. Okay. That's the end of that. So the next thing was 2.23. Let me see where I'm at on time. Okay, we'll stop there. And that was video Organic26A Blake.